The capacitive coupling model for understanding drain-induced barrier lowering offers great insight into why this phenomenon occurs in the first place. So we concluded that drain-induced barrier lowering is a devastating phenomenon that probably at some point in time had the capacity to end transistor scaling. Now we want to consider the first way to view drain-induced barrier lowering, which is the capacitive coupling model. So first of all, consider the difference between a long channel transistor and a short channel transistor. So let's draw an exaggerated look at a long channel transistor, and here we have a source and a drain, and the distance between the source and the drain is the channel length L. If we draw a shorter transistor, a transistor with a shorter channel length, and of course nothing is drawn to scale here, right? This is going to be much shorter than the one on top. Then if we look at L2 and L1, there's a major difference between the two. And the major difference happens to be that one of the dimensions that were negligible in the long channel model is no longer negligible in the short channel model. And that dimension is specifically the depth of the drain and of course the depth of the source, because the device is symmetric. And so if you look at this dimension, xj, which is the depth of the drain, this dimension was negligible in relation to the channel length in a long channel transistor, which allowed us to basically consider the drain and the source to be zero depth, zero resistance terminals. This is not true for a short channel transistor because L is much smaller, and it's now comparable to xj, the depth of doping in the drain and the source. This should make us abandon all the analytical models we developed for MOSFET, because these analytical models depended on solving Poisson's equations and solving field equations that were one-dimensional. In this case, perhaps we should consider the space of the channel as a two-dimensional space, with the dimension xj now coming into play. However, if we keep the original model for current conduction in the transistor channel, we can modify it a little bit by developing an understanding of how the new dimension xj affects it through quote-unquote secondary effects such as DIBL. So let's look at one way in which the drain-induced barrier lowering phenomenon can be understood, and this is the capacitive coupling model. So let's just draw a MOSFET, and again, I'm not drawing it to scale, I'm just drawing the drain and the source to be pretty deep, because this is the thing that basically has caused DIBL to be so clear. So it's not that the channel is short, it's that the channel is short and the drain is now relatively deep relative to that channel. And so we already saw that subthreshold conduction, which occurs in any channel length, so it occurs in long channel transistors and in short channel transistors, that was due to the channel, which is this area, having charges that are controlled by two capacitors. And these two capacitors are fighting for control over the channel. One of them is C oxide, which is the good guy. This is the capacitor we want to have full control over the channel, because we want the gate terminal to be able to turn on and turn off the transistor on its own. But then there is a second capacitor, CDEP, which exists through the depletion zone. So there is a depletion zone under the channel that is formed during the depletion mode of the MOSFET, and then we have C depletion to the body. And so there is a potential divider between these two capacitors, which leads to eta and then S, and then subthreshold conduction. There's a third capacitor as well, which normally doesn't play any role in a long channel transistor, but here it does play a role. And this capacitor is a stray capacitor through the drain, and then through this depletion zone, and then to the channel. And we will call this CD. And so you will notice that the drain has a resistive path to the channel, and it also has a capacitive path to the channel. In a long channel transistor, even in subthreshold conduction, the depletion zone around the drain relative to the channel is very small, and therefore this capacitance is much smaller than this resistance, and its impedance is much higher. And most of the relation between the drain and the channel is controlled by the resistance of the drain rather than by this capacitance, which is what we want to have. In other words, the distance between the drain and the midpoint of the channel in a long channel transistor is very large. And so this capacitor has to go through a very large depletion zone before it reaches the middle point of the channel, which is like the average point of the channel. Whereas here, it's pretty close to the midpoint of the channel, and so CD is going to be comparable to C oxide and C depletion. And so now we have three capacitors fighting for control over the channel: C ox, C dep, and CD. And the problem is, when VGS is lower than V threshold, we expect the channel to be completely relieved of all its charges, to be completely depleted of electrons, but it fails to do so, not only because of C depletion coupling some electrons into the channel, but more importantly because if VD is high, then this capacitance CD is going to couple a lot of electrons into the channel. And this is what we see happening with subthreshold conduction. The drain is causing a lot of electrons to flood into the channel, which represents a failure of the gate to shut down the channel. So how do we combat this? How can we fight this? The main way to fight it is to make C oxide bigger relative to CD, which is exactly the same thing we said in relation to C dep. And so the only way to increase C oxide is to decrease T oxide. And if we decrease T oxide, we increase tunneling current, which could lead to an increase in the total leakage. And so we are in trouble because of this, because of the drain terminal coupling to the channel through CD. And so this is the capacitive coupling model of drain-induced barrier lowering.